Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to this VOC Matric revision program, this session with myself, Muhammad Fasik Peterson. In the next few months, grade 12 learners will sit for the final exams, so preparation is crucial. It not only helps to help learners remember facts, figures, and topics and methodologies, but also, in a sense, just helps them get better acquainted with subjects as a whole. Today, we'll be focusing on chemistry paper 2, and our guest facilitator is Muntasir Kadri, who has a BSc in chemistry and is a private tutor at Intune. Muntasir, Assalamu alaikum and welcome.
Wa alaikum salam wa rahmatullahi wa barakatuh. Thank you for having me.
It's a pleasure, sir. We look forward to this session. I think a very crucial paper. Many might be looking to gain that extra little bit of advice and also just sharpen their knowledge in chemistry. So I think this is going to be a very valuable session. And so I leave it over to you to begin with today's lesson.
Shukran. Thank you very much.
Pleasure.
Okay. So today we'll be doing chemistry paper 2. We'll just be going through some of the long questions, looking at the areas that most students struggle with. So here we start with question 2, and often students do struggle with naming compounds, mainly because they don't really know the rules that apply to them. Or they just don't understand how to apply those rules if they do know them. So the first question here is define the term functional group of an organic compound. Now, a functional group and an organic compound usually looks something like this. Just go here. All right. So you have something like they'll usually be at the end of a compound, and you'll have something like this maybe, right? This would be a carboxyl group. This would be a specific type of functional group. And then another type you'd also have is an OH. This would be what we call an alcohol. Right? These are just some examples. Now, for the specific definition that they give here, if you look at, let me just zoom in for you. There we go, 2.1. So they state here that it's a bond, an atom, or a group of atoms, right, that determines the physical and chemical properties of a group or of a compound. So if we look at this, so for example, alcohol will give specific physical properties to a certain compound, so will carboxyl groups as well. And then you have other various functional groups like aldehydes and ketones and so on and so on. Right? But this is more in your theory. Okay. So if we go on to the next question, question 2.2 over here. So name of the functional group of carboxylic acid. So ironically enough, I just put that up on the board now, and I'll show it to you again. It is this. This is a group that belongs to a carboxylic acid, and this would be your answer, carboxyl. So that would be a carboxyl group. Right? So the name of the group and how you name the compound is usually different. So the compound functional group name would be carboxyl, but if you're naming it in a specific molecule, for example, let's say I decide to go, let's just do methane, right? And then we decide to add this chain on, right? A carboxyl group. Okay. And then something like this would be simply named firstly numbered 1 and 2, right? As they go, Michael eats peanut butter, right? So M is for 1 carbon, E is for 2 carbons, P is for 3, B is for 4, right? This is methane, ethane, propane, butane. So meth, eth, prop, bute. And this specific organic molecule here, we just count the number of carbons first, 1 and 2. And this would mean we are busy with ethane. And at the end of it, we have this functional group, the carboxyl group. So then this becomes known as ethanoic acid. Right? And that's what a carboxyl group does. It usually turns it into an acid. And if we go on to the next question, so we look over here, 2.3. So this is where things get a little bit complicated. They give you these long chains and long names, right? So we have a 2,4-dimethyl hexane 3-one. So we actually have to break this down. So in the first question for this compound, write down the homologous series to which it belongs. And when they speak about homologous series, they're actually talking about the functional group to which it belongs. And we can tell what functional group it is if we just go over here. Let me just get my highlighter. And we look at this, the way this is named. It ends in own. Now, there's a specific functional group that ends in own, and in fact, the name links to this, and that would be ketone. And there's the own in ketone. And that would be your answer for 2.3.1. And then they're asked to go ahead and give us the structural formula for this compound. Okay, and students often get a little bit confused here. Let me just do this. Add it to a new page. Here we go. And if we look at 2,4, dimethylhexanone, we have to break this down into parts. So what each section is telling us, if we look at the numbers 2 and 4 and this part here, dimethyl, what this is telling us is that on the second and the fourth carbon, there are 2 methyl groups, and methyl groups look like this. CH3. Right? That's how we would usually see it. Or if I had to draw it structurally, it would look like this. Right? So this is the 2 methanes on the second and the fourth carbon they speak about. So we know that already. The second thing you want to look for is this over here, hexane. This is telling us about the longest chain that exists within the molecule. Right? And this would mean hexane means 6 carbons. Right? And then we have 3 own. And this is telling us that the functional group for the ketone exists on the 3rd carbon. So if you look at the structure that they gave us, here we can see, okay, 1, 2, 3, 4, 5, 6 carbons. Here we go. That's our hex that we were looking for. Here is our, so if we number these, let me just put the numbers in, it'll help a lot. So if we had to number, this would be carbon 1, carbon 2, carbon 3, carbon 4, 5, and 6. Okay. So this molecule, as we saw, was 2, 4, because of the second and the fourth carbon. There's the 2 methyl groups. Dimethyl. 6 carbon chain, hex. And if we look here on the 3rd carbon, we have the functional group showing. There's the double bond O, and there's the 2 odd groups on the side. So just so you know, a ketone looks like this in the functional group form. Odd, C, double bond O, odd. And what the odd represents is any other side chain attached to the sides of those carbon, to that 3rd carbon there. That's what it's indicating. Any other carbon side chain that's being attached to it. And then that is our ketone group. And that's why we have 3 own. Hence 2,4-dimethyl hex 3 own. Okay. Now, also another thing to note when naming your compounds, and we'll come to questions that add on to it later, but some of the rules, just so I can show you, it's very important. These are, let me just clear this off so I can show you. Let me zoom in. Can I? Oh, there we go. Okay, run out. Okay, so the first rule, the longest chain rule, the parent hydrocarbon must be identified and subsequently named. Okay, so when we looked at the previous molecule, oh yeah, let's go back to it. The longest chain was 1, 2, 3, 4, 5, 6. So that was the hex chain, right? So we'd have from 5 onwards. So it'll go methane, ethane, propane, butane. But then after that, after the 5th carbon, we start going pent, hex, dept, and so on and so on and so on. Right? They add more prefixes depending on the length of the chain. And we got the lowest set of locants. The carbon atoms belonging to the parent hydrocarbon chain must be numbered using natural numbers, okay, which is what we did. It's fairly simple. multiple instances of the same substituent. So as we saw on that chain, we had multiple instances of methane appearing on the second and on the fourth carbon. And that's what they're telling us here. Prefixes which indicate the total number of the same substituent in the given organic compounds are given, such as di, tri, etc. And that's exactly what they did here. They said dimethyl for this one because of the two methyl groups that exist. A naming of different substituents. In the organic compounds containing multiple substituents, the corresponding substituents are arranged in alphabetical order. Often this is forgotten, and this is very important as well. Right? So first, write down all the information you have before you name it so you can see what substituents need to be placed in the appropriate alphabetical order as requested here. And this is a standard naming for nomenclature in chemistry. So this is the standard all scientists will use. The naming of different substituents present at the same positions. In the scenario wherein two different substituent groups are present at the same position of the organic compound, the substituents are named in ascending alphabetical order. Same idea once again. So it's never decreasing alphabetical order, always ascending. And then naming complex substituents. Complex substituents of organic compounds having branch structures must be named as substituted alkyl groups, whereas the carbon which is attached to the substituent group is numbered as 1. Okay, so what they mean by this is usually like if we usually will say methane, methene, or methine, depending on whether or not it's an alkane, alkene, or alkyne. But usually for single bonded alkanes, instead of saying methane, you'll say methyl. Right? Instead of saying butane, you'll say butyl. Hence why they say alkyl groups. So if we go back here, right, and then that was the structural formula for 2.3. 2.4, write down the IUPAC names of the following compounds. So this is where this information comes in handy, these naming rules. So if we go over here and we look at this, just open this up. All right, so we're going to name this. We start with the longest chain. 1, 2, 3, 4, 5, and 6. So that is already, we know that's hex. Right? Hex is going to be somewhere in the name of this chain. Okay, now we look here. On the second carbon, we have 2 methyl groups. Right? So we already know it's dimethyl. And we can say 2. Right? See, there's that alkyl naming rule coming in. I'm ending it with "-ile". Right? So there's our 2-dimethyl. And if we keep looking, we look at the third carbon. No, it's just hydrogen, so we're fine over there. We look at the fourth carbon. There's 2 carbons attached to the fourth carbon. So what does this mean? We look at this group, and we ask ourselves, what would we call this? Michael eats peanut butter. So this is where this comes in again. Meth is for 1. Eth is for 2. Prop is for 3. And but is for 4 carbons. Okay, so here we have 2 carbons. So, and it's on the fourth chain. So now we know we have a 4-ethyl. 2 carbons for eth. So we go ethyl. Okay, fifth carbon, we have a bromo. So now we can say 5-bromo. So there's a bromine there. So, and then the sixth carbon, there's nothing, right? Just hydrogens. Okay, now we have to put this all together. So how are we going to do that? Right? So first, next thing we need to look at is this chain an alkene or an alkyne or an alkane? And we see there's only single bonds on the long chain, on the main chain. So we know it is a hexane. So now we put it all together. Alphabetical order. B is before D, D is before E. So we just go 5-bromo, 2-dimethyl, 4-ethyl hexane. Right? And that's how you would go about naming a compound. Let's just go back over here. Let me clear this off. And there we go. 5-bromo, 4-ethyl, 2,2-dimethylhexane. So my apologies. I made a slight error. This is what happens when you rush things. Don't ever rush things the way I did just here. Right? So I made a slight error in the naming. My alphabet was incorrect. So I looked at the D in the di. Don't do that. That's not part of the letter. It's actually the letter M over here in methyl. So it's 5-bromo, 4-ethyl, 2,2-dimethylhexane. So the methyl goes at the end because M is after E. Right? But if you follow these rules and don't rush it the way I just did here, you'll get it right every time. And if we look at the next question, okay, the next one they want us to name is 2.4.2. And if we look at this molecule, we'll notice something interesting. There's a triple bond over here. So what does that mean? So if you remember from your basic functional groups, you have alkanes, right? You have alkenes, and you have alkynes. Now, alkanes have a single bond on the longest chain. Alkenes have a double bond. And alkynes have a triple bond. Fairly simple to remember, not too hard at all. Alkanes, alkenes, alkynes. And if you look at this, it's a triple bond. So we know that this is an alkyne. So the next thing we need to identify is the longest chain. And the longest chain here is 1, 2, 3, 4, 5. So that means this must be a pentyne. And then the next thing we look at, okay, so we identified longest chain. We identified that it's an alkyne. Is there anything else that's standing out? Yes, there is. There's this over here, a substituent attached to the longest chain. And this is, as we know, a meth group, and this becomes methyl, and it's on the second carbon. 1, 2, 3, 4, 5, 6. So therefore, this would be 2-methyl pentyne, and that's how we go about naming it. Let's just double check the memo. We go down here. Okay, so they named it from right to left. I named it from left to right. This is not a big concern as long as you number your longest chain accordingly, right? So we could have numbered from here 1, 2, or we could have numbered from here 1, 2. Doesn't matter which direction you go in this case, right? Now let's go on to the next question. Question 3. Okay, so here they're speaking about boiling points. So if you look here, the boiling points of some organic compounds are given in the table below. Y represents an unknown boiling point. Okay, so we don't know what this boiling point is. And if we look at the different things we have methanol, ethanol, prop 1-ol, butan 1-ol, butan 2-ol. So all ending in ol. So what this is telling us, these are all alcohols, right? They all have the same functional group. Very important to note, because certain functional groups have certain properties. And if we think about it, this has an OH. So there are special properties that occur between oxygen and hydrogen in this form. Special forces which cause them to stay together, right? And these forces also determine how the boiling point's affected, and so does the longest chain as well. So as we look on, they say 3.1.1, give the structural formula of compound F. Right, so that's over there. So once again, this is nomenclature. So compound F is 2-methyl propan 1-ol. So what can we identify? There is a methane on the second carbon, right? Our longest chain is 4 carbons because this is 3 carbons because this is propan, and we have a alcohol or an OH group attached to the first carbon. Now, if we look at the memo for 3.1.1, that's what we'll have here. There's the methyl group on the second carbon. There's the 3 carbons for the prop, and here we have the alcohol attached to the third carbon. They got it as the first carbon over here. Okay. Now, if we go down, 3.1.2, letters that represent a positional isomer of compound E. So the first question you'd have to ask yourself is, what is a positional isomer? What does this mean? What is an isomer? So an isomer is basically, in this case, that's the same compound, right? Or they'll have the same number of carbons, they'll have the same functional group. So if we had to draw it out in terms of structure, um, this is where they would change. But if we had to look at it just as a number, for example, if it just had to be something like C4, let's just give a random thing, right? C4H6, right? We could have a molecule with different structures, but it can have the same look as this. So for example, if I go C4H6, 1, 2, 3, right? Here we got let's just give it H here, H here. I gotta have another carbon here, right? I can have another one that looks like this, right? And then you can see, let's just say, like I said, this is just a hypothetical molecule. It doesn't really exist. 1, 2, you can see it doesn't exist, right? So there's 6. Okay, let's just give this, let's just give it a double here and a double here. This won't really happen in real life. Okay, so here we go, because here this is defeating the rules. But if we carry on over here, as we can see, the structures are different, but we'll end up having the same amount of hydrogens and carbons here and the same amount of hydrogens here. And that's basically what an isomer is. So different structures, but same molecular formula. Now, if we go back to this problem, 3.1.2, letter that represents a positional isomer of compound E. If we look at compound E, which is butan 2-ol, okay, if we draw this out, and that's how we would have to answer this. We got 1, 2, Michael eats peanut butter. We know that the alcohol is on the first carbon, so we can just put that over here. We call that the first carbon, right? And that's basically it for, oh, sorry, butan 2-ol, not 1-ol, butan 2-ol. Right? So if we look here, here's our molecule. This is compound E that we just drew. But now, which one would be the isomer? So if we look at these, which one is closest? So first of all, we're going to look for another but, and we can see that the only place another but exists is D, butan 1-ol. So if we had to draw this one, our alcohol functional group would be over here. So there we can see same molecular formula, which is going to be C4, 1, 2, 3, 4, 5, 6, 7, 8, 9, H9O. This molecular formula is going to be the same one for this one over here. But as you can see, they're isomers, positional isomers. And why are they positional isomers? Because the position of the functional group of the alcohol has shifted from position 2 to position 1. Right? That's what's happened here. Now, we can just double check on the mirror, see if we are correct. And if we look over here, the answer is D, butan 1-ol, right? And that's how you would go about trying to answer a question like that. Now, let's go on to the next one. So, again, we're speaking about isomers, and they say 3.1.3, letter that represents a chain isomer of E. Okay, so a chain isomer of E. So a chain isomer means the chain is different. So what we are looking for then is we're still looking for the same molecular formula, which was C4H9O, or in other words, to make it actually look proper so you can see the function, H8OH, right? This is what we are looking for. Now, if we look around, let's see, what would have 4 carbons here? Not meth, not F, not prop, not but, not but. So it's either going to be F or it's going to be G. One of these two. Now, let's see if we can identify which one it's going to be. 2-methyl propan 1-ol. Okay. Let's see if we can find which one it is. Actually, it could even be C because it's propan 1-ol. But let's take a look. So we've got, if I I go here, let's check the memo, and they say it's G, 2-methyl propan 2-ol. So let's take a look at why they said it's G. And we can go here, prop 1, 2, 3, Michael eats peanut butter, so 3, okay? And there's a 2-meth. So we know we've got a meth over here, so there's the C. And 2-ol, okay? So on the same carbon is the alcohol. And let's see if it all matches up. So this is CH3, this is CH3, and this is CH3. Let's see if it all adds up. Because remember, we were looking for C4H8OH, H9OH. That's what we were looking for, C4H9OH. And if we look here, we have 3, 6, 9 hydrogens over here. There's our OH group already sitting. There's OH. And here's our 1, 2, 3, 4 carbons. And this is a different chain compared to butane 2-ol. Because if we look at this structure again, 2 alcohol. This is a H there, H3, H3, H3. And then we can see 3, 6, 9, right? Sorry, maybe this is a 2. 3, 5, 8, 9. These are 9 hydrogens. There's our alcohol, and there's our 4 carbons. Right? So, as we can see, this is why they are chain isomers. The chain is different. The way the main chain looks is completely different. But the molecular formula is the same. Now, let's look at the next one. 3.2. Oh, excuse me, let me clear this off. 3.2. The boiling points increase from compound A to compound B. Give a reason for this increase in terms of the molecular structure. So, in terms of molecular structure, what they are speaking about is basically the sizes of the chains. And if we look at these molecules, okay, they say, give a reason for this increase in terms of molecular structure. We can see methane only has 1 carbon, ethane has 2, propan 1-ol has 3, butane 1-ol also has 4, E also has 4, but the position of the alcohols are different. And that kind of causes a slight difference in temperature. As you can see, butane 1-ol is greater. But if you look at the others, if we go to F and we go to G, right, all of a sudden, there's a massive jump over here. Well, not really massive, but we can see 82.5. So there's a decrease from butane 2-ol. Right? So what your answer would usually be for something like this is you just say it's got to do with the basically the number of carbons or what the size of the longest chain is. Because usually the heavier the molecule is, the higher the boiling point is going to be. And if we look at, excuse me, if we look at, I don't know what happened there. Let me just go back here. If we look at the answer to that, 3.2, so there we go. Increase in chain length, as I mentioned, molecular size, molecular mass can play a role. So molecular mass is determined by sometimes heavy substituents are added onto side chains, like maybe bromine or chlorine will be attached to a side chain, and that can also increase the boiling point. The number of carbon atoms, so I mentioned that as well. Because obviously carbon atoms, as we know, they weigh 12 grams per mole, and the more carbon atoms you have, the more those molar masses are going to add up. The surface area is very important as well. Obviously, if you have a large surface area, you'll be able to have a lower boiling point. But the smaller the surface area, the higher your boiling point is going to be, because it's going to take a lot more energy to get down to all the molecules within the structure itself, right? And then contact area, which is kind of similar to surface area, and then the number of electrons. Okay, so these are all possible answers which would give you 1 mark and it would be correct. If we go to this question over here, 3.2.2, name the intermolecular forces in these compounds responsible for this increase. Okay, so they're not asking about intramolecular, they're asking about intermolecular. Right? So these are forces that exist between molecules themselves instead of forces that exist between different atoms. Okay? So for intermolecular forces, you will have things like, and I'll just show you over here, London forces, dispersion forces, and induced dipole forces. Now, there's also induced dipole. There's also there's all different types of forces that exist between intermolecular molecules, and this can be confusing sometimes. So this is some theory that's important to go over. You don't get much questions on them, but they are important in understanding how molecules work and what energies are required to break certain bonds. Right, so London forces are actually your weakest forces, and there's also your van der Waals forces, and so on. And if we go to 3.3.1, they say it's 108 degrees centigrade, but let's just see why. So they say consider the boiling points given below: 85 degrees centigrade, 108 degrees centigrade, and 122 degrees centigrade. From these boiling points, choose the boiling point represented by Y in the table above. So they say 108. Right? There's jump over here. Right? And well, my reasoning from the information that's given here, I mean, if you look at butane 1-ol, we've noticed that if the alcohol exists on the first carbon, then the isomer of that molecule, the positional isomer with the alcohol on the second carbon, actually has a lower temperature. But why is that? Why does that change in structure cause that decrease in temperature? And we can therefore reasonably assume that if we look at this, it's the exact same molecule, it's just that it's a positional isomer. So this one has its alcohol on the first carbon, so therefore we could assume that this Y would be a higher temperature than this 82.5 over here. And if you look at the options given, 85, 108, 122, it's not a massive difference. Right? If we look at the difference between this and this, 99 to 117, it's about 17 degrees difference. Okay, and we could make about the same assumption here. If we add on 17 degrees here, we'll get about 99. So 108 is a lot closer than 102. Right, so there's a reasonable assumption to make there. So then they fully explain how you arrived at the answer to question 3.3.1, and this is where you're going to have to discuss, of course, how the position of the functional group affects the change in temperature for boiling point. And we'll look at that now. What would have caused these changes? So, compare compound F, compound C, and D, which is what we did. Right? So if you look here, the state compound F has a larger molecular mass, molecular size, surface area, contact area, number of carbon atoms than compound C. Right, let's just go back here, see what they're speaking about. So we go back here, and then we're comparing compound C, compound F over there. Right? And we can see here, compound F is going to be a lot bigger. Right? Here we've got Michael eats peanut butter. So here we got 3 carbons. Here we have 4 carbons because here we have 3 on the prop, but an extra 1 coming from the methyl. So of course, that's going to have a higher boiling point than that, just based on the number of carbons alone. And if we go back here, compound F is more branched than compound D. So there's another reason for the increasing in boiling point. The more branches a compound has, the higher the boiling point will be. So if we look here, so they're talking about F and D in the specific example. So if we go here to F and D, we compare the two. Clearly, they have more branches. Right? This molecule has a main propane chain of 3 carbons and then a side chain on the second carbon of 1 methyl group. Whereas the D only has carbon, 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 carbon. So 4 carbons, but all in a straight line like this. That's D. But this one is 1, 2, 3, but there's a side chain. And this branch, this extra branch, what does it cause? There's more area for contact to occur. Right? It's increasing the contact area, whereas this contact area is kind of limited due to its straight chain structure. Now, clear that off. Right. And the rest of the reasons, we just quickly browse through that, and we look at the rest of the reasons. Intermolecular forces in compound F are stronger than in compound C and weaker than in compound D. Why is that? F is stronger than C and weaker than in compound D. Let's see, what is the reasoning? Okay, here we go. Did they say, let me just double check, was C stronger than F? Sorry about that. F, oh yeah, sorry, F is stronger than C. Okay. So F is stronger than C. So if you look here, so in terms of intermolecular forces, yes, this is a longer chain. We have more molecules. So if we add up the values of intermolecular forces, this is going to be greater, right? And then if you look at, and then they were comparing it to compound D over here, right? So, and the last one, the more energy needed to overcome intermolecular forces in compound F than in compound C, and less energy needed to overcome or break intermolecular forces in compound F than in compound D. So this is why I say it's important to understand your intermolecular forces. Now, I don't really have time to go in detail about all the intermolecular forces. It really takes quite some time. Right? But if you do read up some theory on it and really put your nose to the grindstone, this will make a lot of sense to you. Right, so let's look at the next question. We go down, we pass boiling points. Okay, 3.4. Hydrogen bonding is responsible for the relatively high boiling points of compounds A to G in comparison with hydrocarbons of a similar molecular size. Hydrogen bonding, let's see this again. So you need to understand the idea of hydrogen bonding. And hydrogen bonding occurs between specific atoms, and it usually occurs between oxygen and hydrogen, nitrogen and hydrogen. These are the two most common compounds that you'll find hydrogen bonding in. Is responsible for the relatively high boiling points of compounds A to G in comparison with hydrocarbons of similar molecular size. They say draw two structural formula of compound A. Use a dotted line to show the hydrogen bonding between the two structural formula. So here they're looking at compound A, and let's just quickly take a look at it as well. Let's go here. Compound A in 3.4. So here we go. So once again, they're speaking about intermolecular forces, right? Not intra. So yes, there's intermolecular forces that exist between the hydrogen and the oxygen here, right? This is between our atoms, but then we have intermolecular, which is forces that exist between molecules, and this molecule here is interacting with this molecule here, and this dashed line is representing the hydrogen bond that exists between the oxygen and the hydrogen of the two different molecules, and this here is methanol. So the oxygen of this methanol is interacting with the hydrogen of this methanol. And the thing is, the more methanols you have, so methanol is a liquid, and what will happen is we'll just end up having a lot of these molecules in liquid form, having all these hydrogen bonds keeping them together. Right? And this is actually the same for water. This is also why water has such a high boiling point. If you think about the water molecule, it looks something like this. Right? Here's water molecule. Right? And obviously, this is one water molecule existing on its own. But when you pour yourself a glass of water, there's many of these molecules in your glass. And the reason that water has a high boiling point and is able to have the water tension that it does and all its special properties is because of these hydrogen bonds that exist between different water molecules. And this will just go, it'll go on forever, right? Amongst all water molecules, and it'll keep doing that, and it'll just make a lovely looking pattern once you've done a lot of them, but I'm not going to go through all of that. So let us look at the next question. Question 3.5. Here we go. Right. Compound B reacts with propanoic acid in the presence of concentrated sulfuric acid. Write down the type of reaction that takes place. So we got propanoic acid reacting with sulfuric acid. So in order to actually solve this problem, we need to know what these molecules look like. Right? We need to know what these compounds are. So if we go to the memo, let's just take a look here. And okay, so they don't give us the molecules, but they do tell us that the reaction that occurs is condensation or esterification. And so what we end up getting is an ester. So let's actually take a look at what this reaction is. Let me get to the two molecules. So we got propanoic acid and sulfuric acid. Let me just here, propanoic acid. Trying to get the molecule quickly. Okay, and there we go. So it is a carboxylic acid. Right. So just go back here. Let's take a look at these two. So sulfuric acid is H2SO4. Propanoic acid, as we saw, is 1, 2. Michael eats peanut butter 3, right? And we can say there's the double bond, there's the OH. Okay. So in esterification, we actually form an ester. And what we'd have is end up having is sulfuric acid reacting with this, right? And we would end up with a special type of ester. And usually esters, if you look at the functional group, just show you here quickly, the functional group of esters, CORR double bond O. So what's essentially going to happen here, if I just go back here, it's tidy, right? We're supposed to end up with C double bond O, OR, and some R group attached to this over here. Okay. So what's actually going to happen is this double bond O is going to stay here. This oxygen is going to bond itself to another carbon group, and we're going to have this chain running off of the side here. Right? So we can't really do this reaction. This is actually kind of a weird question, honestly. I feel like this is supposed to be alcohols it's supposed to be combining with. Sorry, let me just check something for you quickly. Esterification. Let's just see. Is a chemical compound? Yes, I'm correct. At least one hydroxyl by an alkyl or alkyl-oxyl group. Yes. Combining an organic acid with an alcohol. Yeah. So this question, there's actually an error in this question. I thought something was weird. So this isn't an esterification type reaction. I thought something was weird here because, first of all, propanoic acid is not an alcohol. It's a carboxylic acid. And this over here is an acid. Right? And esterification actually takes place. If you're going to form an ester, it occurs between an alcohol and a carboxylic acid. Then we'll get an ester. So there's actually an error in this question on this memo, unfortunately. Right? So we'll have to re-look at this one or find a properly designed question. Right? But this is where you will form esters between an alcohol and a carboxylic acid. I was wondering why I was getting so confused there. It was so weird. Right? And this will give us an ester. Okay. So as you can see, there's quite a bit of work in naming and just in the bonding itself. Right? There's a lot of information that needs to be understood here and a lot of theory that needs to be understood with regards to intermolecular forces and intramolecular forces. And that also leads into the different shapes of your molecules, bipyramidal, tetrahedral, octahedrons, and so on. Right? So it's a lot of theory to take in, but it is important. As we saw, just for the section, that was 17 marks. Just 17 marks alone, just based off of intermolecular forces. And this was 30 marks alone, just based off of structure. Now, unfortunately, I would love to go on further with you, but I think we've run out of time. Right? And I would love to go further with you and then carry on with this flow diagram, because this leads us more into how structures and the different compounds are formed. And this is also with major adducts, major products. So I'm not going to waffle on. But yeah, we'll end there for now. Shukran very much for joining me. And I hope everyone has learned something today and you enjoy the rest of your day as well. Shukran. Assalamu alaikum.
وعليكم السلام ورحمة الله وبركاته. Shukran so much to you, Muntasir, for sharing knowledge with us and helping prepare our matrix for chemistry paper. And of course, you're welcome to check out the broadcast if you missed it live on YouTube and Facebook after. And of course, Mutassi will be joining us again tomorrow as we look at mathematics. That'll be the theme for tomorrow. If people want to get a hold of you, you are a tutor in your own capacity, how can they do so?
Well, they can contact me on my mobile number. That would be 071 92598. Or they can email me at philomathtuition@gmail.com. That is PHILOMATH, tuition, TUITION @gmail.com.
And that cell phone number again is?
071 925 9598.
Shukran so much, Muntasir Kadir, for joining us. And we look forward to tomorrow's session.
Okay, shukran. I look forward to that as well.
Shukran. Jazakallah khair. Walaikum salam wa rahmatullahi wa barakatuh. And of course, that has been it for our matric revision for today. Once again, just a look at what's coming up. The subjects will be covered. Tomorrow we'll be looking at mathematics, Wednesday business studies, Thursday English, and Friday will be Arabic once again with our very special guest, Sheikh Nasr Barnes, inshallah. Ameen. And of course, as we mentioned, you are welcome to check out the sessions live on YouTube and Facebook when we stream them, or thereafter you are welcome to go back and check out the video. And also, if you're not a matriculant yourself, but you know of matriculants that could benefit from this, please do share far and wide. Share the link, share it on Facebook, share it on YouTube, or copy the link and share it on whichever other platform you feel might be useful. We know matriculants need all the assistance they can get, and so we invite you to share these videos far and wide. They remain up on Facebook and YouTube. Well, from myself, Muhammad Fasiq Peterson, until I speak to you again, inshallah, I bid you assalamu alaikum wa rahmatullahi wa barakatuh. Have a safe and fantastic day further, and of course tune in tomorrow around about the same time as we once again engage on matric matters. This time around, of course, tomorrow we'll be looking at mathematics, a very, very important one. So please do join me live early, and of course also you're welcome to share it thereafter.